The article I chose is called Sedimentation of C60 and C70, Testing the Limits of Stokes' Law. And the authors are Joseph Pearson, Tig Nguyen, Helmut Kolfin, and Paul Mulvaney. And the article is from the Journal of Physical Chemistry Letters. And as a quick note, all the figures and equations shown in this presentation are directly from the article. As we learned in class, the Stokes-Einstein equation is often applied to determine particle size by using the diffusion coefficient d, obtained from analytical centrifugation, to calculate the Stokes radius, which is just the apparent radius of a molecule sedimenting under centrifugal force. The objective of this article was to experimentally test the validity of the Stokes-Einstein equation on a nanoscale regime under non-slip boundary conditions. Boxed here is a Stokes equation derived from Stokes' law, where we assume spherical shape of the particle. Kb is the Boltzmann constant, T is the solution temperature, eta is the solvent viscosity, R is the radius of the particle, and F is the frictional factor. Researchers measured the sedimentation and diffusion coefficients of two types of fullerenes, C60 and C70. We briefly mentioned what fullerenes are in class, but they are one of the three forms of carbon, and it consists of carbon atoms forming closed or partially closed cage-like structure. C60 and C70 are arranged as hollow spheres of 60 and 70 carbon atoms, respectively. Nevertheless, the measurements were conducted in toluene as a solvent using analytical ultracentrifugation, and the experimental sedimentation rates and diffusion coefficient values of the fullerenes were compared to the results of the Stokes equation. And compared to typical analytical centrifugation, analytical ultracentrifugation uses much higher speeds for the separation process. To calculate the diffusion coefficient of the fullerenes, assuming a spherical shape, the researchers used a slightly modified version of the Stokes equation from what we saw in class. The biggest difference is that the shape factor F over F naught is included in the denominator to account for any non-spherical geometry. Even though the equation itself assumes spherical shape and the C60 and C70 molecules have spherical geometry, the frictional ratio is there to take into account any small deviations from that assumption for improved quantitative accuracy. And per their notation, they use an A instead of an R for the Stokes radius I mentioned earlier. Now here's the equation they use to calculate the sedimentation coefficient. The equation looks much different from that of our class material, but its derivation is shown right here, and it's rather straightforward and uses equational components that we have already seen. So since the forces acting on a particle in a centrifugal field are the centrifugal, buoyancy, and frictional forces, which is illustrated on the top right, we can set up a mechanical force balance of those three forces. From our equations, we know that the frictional force, assuming spherical shape, is equal to 6 pi eta times the particle radius and velocity, and the centrifugal force equals the particle's effective mass times the centrifugal acceleration, which is the angular velocity of the rotor squared times x, the distance of a particle to the rotor axis. Then the centrifugal buoyant force is equal to the particle's volume times solvent density times the centrifugal acceleration. After plugging all of that in, we can substitute 4/3 pi r cubed for the particle volume since we are assuming spherical shape, and then solve for velocity. And finally, we know that velocity, or the centrifugal acceleration, equals the sedimentation coefficient. So the researchers in the article express the sedimentation coefficient using only radius, viscosity, and density values. It is different from the sedimentation coefficient equations we have seen, because most importantly, this equation allows for the diameter of the fullerene molecules to be determined independently from the particle's mean sedimentation speed. So fullerenes, particularly C60 and C70, are useful and highly reproducible probes for both analytical ultracentrifugation, calibration, and validating the Stokes equation for accurate nanoscale sizing. And the Stokes-Einstein equation provides a consistent explanation for the observed sedimentation speed and the diffusion coefficient of C60 and C70, assuming non-slip boundary conditions. As shown in this table, using analytical ultracentrifugation, or AUC, they calculated a radius of 4.83 angstroms for C60, assuming non-slip boundary conditions, which is in agreement with the average radius determined from several other methods in the literature. And A sub d in the column header just stands for the calculated particle radius based on particle density. So I chose this article because I was curious about how results from the Stokes equation would change at nanoscale particle sizes, but also fullerenes are relevant to my own research in organic solar cells because they are used to make devices, So when seeing the article title mentioning fullerenes, I was interested to see how they were being used to test Stokes' law. Thanks for listening.